without getting into the details, fatty acids, if converted into two carbon molecules called acetyl-CoA, they make their way into the Krebs cycle, which can be used to generate energy. So aerobically, we can break down both sugar and fatty acids using oxygen to generate a lot of energy. And definitely, if you're doing light exercise, this is your dominant mode of metabolism. We're doing everything aerobically. If you're doing some endurance workouts, you're focusing on your aerobic metabolism. As I mentioned, it can be very beneficial in individuals with type 2 diabetes, certainly in individuals that might be prone to developing type 2 diabetes. Exercise can help to delay the onset of type 2 diabetes. Because, well, as we'll see in chapter 11 in more detail, we get the GLUT transport. We've seen GLUT transporters, right? GLUT transporters, they're allowing passive transport glucose into cells. We get more and more of those in the T2-fuels of our skeletal muscle. Our skeletal muscle takes up glucose more and more efficiently as we train and we're doing more exercise. So that can really help our efficiency of aerobic respiration. It can really help our VO max, having more of these GLUT transporters. Our skeletal muscle also has the ability to store extra oxygen in a form called myoglobin. We'll be looking a lot at hemoglobin in our upcoming chapter on the blood. That's coming up really soon, and we'll see how hemoglobin binds and transports oxygen to the different tissues of the body. Well, in our skeletal muscle, we have a molecule that is hemoglobin-like. It's called myoglobin. It can bind oxygen and help our muscles store that oxygen for future use, and that can help with our aerobic respiration. But if we're working so hard that the amount of oxygen and the amount of glucose and fatty acids that we're getting aren't sufficient to keep powering our exercise, we're getting into our medium to high intensity exercise, now we start to see our cells ferment. We're hitting our lactate threshold, and our cells begin fermenting. And again, this is an anaerobic type of metabolism. It's not anaerobic respiration, but it's a relatively inefficient way of generating energy when there's not sufficient oxygen present. It's inefficient, but it's better than nothing. I mean, if there's not enough oxygen there, aerobic respiration is going to stop. This gives the cell an extra boost of energy that it can produce when oxygen levels are sufficient to provide enough power. Glycogen especially can be used to power moderate and heavy exercise. One of the things that you develop in your skeletal muscle as you do more and more of endurance and heavy exercise, you start to store more glycogen in your skeletal muscle. Your skeletal muscle becomes more efficient at storing glycogen and powering this exercise in the future. Remember, glycogen is a storage form of glucose. Glycogen is essentially a long polymer of glucose. And when our skeletal muscles are exercising, that stored glycogen can be broken down into glucose. That glucose can be used either in aerobic respiration, or that glucose can be used for fermentation. Both of which are going to provide energy and ATP for the cell. So as we're putting more and more demands on our skeletal muscles, we're going to start using glycogen as a major source of glucose so that we can perform aerobic respiration and fermentation. Keep in mind that fermentation, again, in our bodies, produces lactic acid. From the perspective of skeletal muscle, that lactic acid is a waste product. There's nothing directly that the skeletal muscles can do with the lactic acid. But the lactic acid, when it is produced by skeletal muscles, it can make its way in the bloodstream to the liver. The liver can then convert that lactic acid back into glucose. It can be used in the future to generate energy as well. It's not totally a waste product. There's still energy in that lactic acid. The liver will recycle that lactic acid so that it can be used as a source of glucose for additional energy. That's a level of biochemistry I don't want to get into here. There's just not a lot of time. But if you take a biochemistry class, you'll see how lactic acid can be converted back to glucose and used as an energy source in the future. And then a third molecule that can be used to generate ATP by the cell is phosphocreatine. This is a supplement. You can take creatine supplements. Typically, if you're taking a creatine supplement, you're thinking about doing high intensity activity that doesn't really last a long time. You're thinking about weight training for creatine. Creatine probably doesn't help you much at all if you're doing endurance type activities. What creatine does, you can see in muscle cells, looking at this figure, when muscle cells are at rest, they can take phosphate from ATP, stick it onto creatine, they make phosphocreatine. So when your muscle cells are resting, they're producing phosphocreatine. Phosphocreatine builds up in our muscle cells. When we start working out, that phosphocreatine can quickly be used as a source of phosphate. The phosphate gets stuck onto ADP. We make ATP that powers muscle contraction. So you can think of phosphocreatine as a storehouse for phosphate that can be used to make more ATP in the cell. It's kind of a quick energy source. We're talking maybe 10 or 15 seconds worth of energy in phosphocreatine in muscle cells. It's helpful for a quick burst of energy, but it's not going to help you run a marathon or cycle any distance.
So we gotta have to do like more repetitions or?
It can help you extend to a few more reps, a few more powerful reps. If you're taking a creatine supplement, you get more creatine in your muscle cells. You boost up your phosphocreatine levels a little bit more. It helps you with reps. It helps you with doing really powerful contractions. Kind of gives you a kick as far as muscular contraction. We synthesize this stuff naturally. You'll make creatine. Your liver and kidney make this, or we can obtain it as a supplement. And it's creatine kinase that's transferring this phosphate, giving us ATP. So that's a quick, short-term solution for a burst of energy, that phosphocreatine. But again, typically if we're doing exercise for long periods of time, we're looking at aerobic respiration, and then as we get towards our VO max or our anaerobic threshold, we start to kick in for metabolism. When you get done exercising, typically you're out of breath. You know what I'm talking about. You're panting, you're out of breath. And when you get done exercising, you're still out of breath. It's not like, okay, I'm done exercising and my respiratory rate goes back to normal immediately. It doesn't work that way. You've got a period of time where you're struggling to catch your breath. And you get better and better at it as you get more well-trained doing exercise. But there's always this lag time between when you stop exercising and your respiration goes back to normal. What's happening here, Paul talks about this a bit, you are doing your recovery oxygen consumption. You're paying off what we call the oxygen debt. So what's happening, when you're paying off that oxygen debt, you're taking in, you're breathing heavily, you're bringing in more oxygen than you would at rest into your body. What we're doing is starting to store more oxygen, especially in our myoglobin. We're delivering oxygen to our muscle tissue, and we're delivering that oxygen to myoglobin. Myoglobin can find that oxygen, we can build up our reserves of oxygen in our muscle tissue. We're making sure that hemoglobin in our blood is fully oxygenated. As part of paying off the oxygen debt is storing oxygen for future use in our myoglobin. Another thing that happens, if you've been really working out hard and you've been beyond your VO max, you're in your anaerobic zone, and you're fermenting, you're producing a lot of lactic acid. It requires oxygen. The liver needs oxygen in order to metabolize that lactic acid back into a useful form. So you're breathing heavy, helping to get that liver converting that lactic acid back into something useful for the body. That's also an increased energy demand. And so it takes a while after you stop exercising for that respiratory rate to finally get back to normal. We're paying off this oxygen debt with increased consumption, heavy breathing, for a period of time after we work out. Y'all know what I'm talking about. You run, do anything physically, breathe heavy, and it takes a little while to recover. So they're looking at recovery. One of the things your book likes to talk about, and it presents these as one or the other. In reality, there's a spectrum of muscle fiber types. We're looking at opposite ends of that spectrum. Certainly, any given muscle fiber might share some of these characteristics, some of the slow twitch or some of the fast twitch characteristics. If we look at our muscle fibers as being one or the other, the opposite ends of the spectrum, we can view our muscle fibers as functioning as slow or fast twitch muscle fibers. So what we're looking at, when we look at these different types of muscle fibers, we're looking at what type of myosin. There's actually different types of myosin that we can find in our skeletal muscle. We're looking at how much myoglobin do we have, how much blood supply do we get, what type of activities are these given muscle fibers useful for. Not all muscle fibers in a given skeletal muscle have all the same qualities. We'll see differences between these muscle fibers. At one end of the spectrum, we have our slow twitch fibers. I don't care if you memorize type 1 or type 2, I'm not going to use that. Your book mentions it. But if we look at our slow twitch fibers, these are fibers that, well, as the name implies, they contract slowly relative to our fast twitch fibers. The twitch takes a little bit longer to contract and then to relax. We don't have as vigorous of a twitch in our slow twitch fibers. Generally speaking, your slow twitch fibers have a very, very good blood supply. So they're getting a lot of glucose, plasma fatty acids, as well as especially oxygen from the blood. So they've got an ample blood supply. Because of this, because of their slow twitches and that great blood supply, they don't tire out anywhere nearly as rapidly as a fast twitch muscle fiber. These are typically slow to fatigue. These are muscle fibers that are really good for endurance activities. So if you're doing long-term endurance activity, you're running a marathon, these are the types of muscle fibers that you're dealing with. You're dealing with these endurance fibers. These are the same fibers that we're using to maintain our posture, right? I can stand here throughout the course of this class. It's 100 minutes that we're here in class. I'm not going, oh my God, I'm so tired. I've been standing for so long. I gotta lay down. These fibers are able to maintain my posture for a relatively long period of time. That's endurance. I wouldn't mind sitting down right now, but I can deal with this. We got a lot more mitochondria in slow twitch fibers. A lot more mitochondria. Why are mitochondria important? They're producing energy. They're doing aerobic respiration. So when you see mitochondria, this is the site of aerobic respiration. So we have relatively high aerobic capacity of our slow twitch fibers. Not only are they getting more oxygen from the blood, they have more mitochondria to use that oxygen, so they're going to have a very high aerobic capacity. I like food. Lots like food. Think about drumsticks. What kind of meat do we see in our chicken in the drumstick? Two kinds of meat. Starch. Drumsticks have a darker pigmentation. If you look at chicken breast versus the drumstick, darker meat in the drumstick, it's because we see a lot more myoglobin. Hemoglobin has a pigment. Hemoglobin has a reddish pigment. So does myoglobin. So we see a lot more myoglobin in these muscle fibers. They're enriched in the leg muscles of chickens. They're good for endurance activities, for maintaining posture, for moving about, walking. A lot of myoglobin, again, oxygen storage. These are great muscle fibers for aerobic, long-term endurance, energy-demanding activities. The myosin heads break down ATP relatively slowly, which is leading to the slower twitch. It leads to that slower contraction, relaxation. So, if you want to do some endurance activities, you want to go run a marathon, you're training slow twitch fibers in your muscles. If, on the other hand, you're thinking about weightlifting, you're thinking about swinging a baseball bat, hitting a ball really far, you're thinking about sprinting, we're talking about short-term, high-intensity activities. Now we're relying predominantly on a different type of muscle fiber. These are the fast twitch fibers. And any given individual in the population has a different mix of slow and fast twitch fibers. It can vary from person to person. Some of us are better suited for endurance activities. Some of us are better suited for short-term power activities, right? Some of us are sprinters. Some of us are marathon runners. That has a lot to do with the dominant type of muscle fibers that we see in our muscles, and also how we train our muscles. But if we look at our fast twitch fibers, they contract rapidly. We've got a quick, powerful twitch. That's because myosin breaks down that ATP very rapidly. So our sliding filament theory works a lot quicker in these cells. They do have less blood supply and fewer mitochondria. So they're going to hit an anaerobic state much more rapidly than a slow twitch fiber is. They're much more dependent on fermentation, anaerobic metabolism. Because of this, they run out of energy and fatigue much more quickly than a slow twitch fiber. You're not depending on these fibers when you're running a marathon. These are great for rapid, intense movements, like punching or swinging a baseball bat, or sprinting, or weightlifting. There you're looking at fast twitch fibers. They have a relatively low level of myoglobin. They're not storing a lot of oxygen. Again, primarily we're looking at anaerobic metabolism in these fibers. Think about chicken breast. If you look at chickens don't really fly anymore, but they will flap their wings every now and then to kind of get away or scare off a predator. They don't flap their wings for long periods of time. This is a quick, intense activity, and they tire out really quickly from flapping those wings. It's those breast muscles that are primarily fast twitch fiber containing muscles that are responsible for the chicken wing flapping. So just kind of a way to remember those two different types of fibers. Again, the way this is presented in the textbook, it makes it sound like muscle fiber is one or the other. In real life, this is a spectrum, where we'll see muscle fibers that are way over here on the slow twitch end of the spectrum, and then we'll see hybrid muscle fibers that have characteristics of both. They're not as great as either, they're kind of in between, and then we see our fast twitch fibers that have these fast twitch. So don't look at it as a fiber as either one or the other in your body. Often there are kind of hybrids in between these two extremes. In a sense, nothing is ever as simple as it is in the textbook. In your think that we are all familiar with is the idea of fatigue. Our muscles are getting tired, they start to wear out when we're doing exercise. This is essentially a decreased ability to perform, to do work. You start to see your performance, your ability to do work decrease as you begin to fatigue. Now, muscle fatigue isn't terribly well understood. There's a lot of things that can come into play that can cause muscle fatigue. First off, if you've been doing really intense exercise, you can start to see an ionic imbalance across the cell membrane where you see extra potassium outside of cells, which we wouldn't ordinarily see. This typically is relieved very quickly, this ion imbalance. How do we fix this ion imbalance? There's a lot of potassium outside of our cells. What fixes this? The sodium potassium pump. That's going to take over. So this gets fixed up really quickly. But if you've been doing a lot of exercise, you've been working hard, if you have a lot of potassium outside of your cells, let's think about this. How could this negatively impact the function of our cells? Remember, when a muscle contracts, it's generating an action potential. What's the first step in generating an action potential? You hit a threshold. You hit threshold, what occurs? We see sodium flooding in the cell. There we're depolarizing our cell. And we certainly see this when a muscle cell contracts. We generate action potentials. We have depolarization in our cells. What happens after those sodium channels close? We repolarize. What causes repolarization? Potassium going out. Now here's where the problem is. We're looking at potassium going out of the cell. If we have a lot of potassium that's already out of the cell, we don't have a stable concentration gradient. So what can happen? If there's a lot of potassium outside of our cells, we're not going to see potassium exiting the cells quickly. We're going to slow down our repolarization. Our muscles stay depolarized longer and they're contracted longer. How does that manifest? What do we feel? We feel cramps. We've got an ion imbalance where our muscles are failing to repolarize properly. This ion imbalance leads to cramping, and I would think that we would all agree. Would we all agree that cramping leads to a decreased capacity to do work and a reduced efficiency of performance? That's part of fatigue. Typically, this gets fixed relatively quickly. You can think about a soccer player. They're cramping up on the field. They're drinking water. They're stretching out. They can get over that cramp. I mean, it's not like immediately, but we're talking on the order of minutes. That cramping typically gets taken care of in most cases. Sometimes the cramping is so severe, it's the end of the game for that player. But generally, this isn't going to cause you a long-term problem. Our bodies can fix this issue relatively quickly with proper hydration, taking in electrolytes, and just stretching. Other things that happen with muscular fatigue, if we deplete glycogen, why would that be a problem? What? You've got less energy. Glycogen starts to get depleted in our muscle cells. Well, there's less energy reserves to call upon. There's no energy. You're not contracting your muscles. That's one of the things we gain when we're doing endurance training. We begin to store more and more glycogen in our muscle cells. That makes us capable of doing activities longer and stronger by having more of that glycogen. What happens if calcium builds up in our cytoplasm? What's that essentially happens? We're going to have prolonged contraction. That leads to exhaustion. But if there's all this calcium that's always there in my muscles, in my cytoplasm, what is my muscle going to be doing? It's going to be contracted. That leads to fatigue and cramping. So we've got a high level of calcium. Remember, it takes energy to move that calcium back to the sarcoplasmic reticulum. As we start running out of energy, if we can't re-sequester or transport that calcium back into the cytoplasmic reticulum, we're not gonna see relaxation, and we're gonna have cramping starting to occur. So that can be an issue, that can be a longer term issue because it requires energy to fix that problem. Excess phosphate in the cytoplasm, we have excess negative charge in the cytoplasm, that can cause some issues. Sometimes, and this is a real big thing that people talk about in exercise physiology, there's this focus on lactic acid. It's thought, oh, maybe we get a lower pH from lactic acid, it's building up in our muscles. I really would question that. Lactic acid is not a terribly strong acid. Whether that's really going to impact the pH of the cytoplasm, the tissue of our muscles, it's really, really questionable. Another thing that you hear a lot about talking about exercise is they will say, I hear it all the time from the trainers on my exercise bike, they say, oh, that burning, that soreness that you're feeling in your muscles, that's from lactic acid buildup. There's really no evidence that supports this. If you talk to an exercise physiologist that's really in the know about what we know about exercise, there's no evidence that lactic acid is causing that soreness that you feel after working out. Most likely what you're dealing with when you feel sore after a workout, you're talking about microabrasions in the muscle with micro tears, there's a lot of stress on the muscle. Remember, it's rubbing across bone and other connective tissue, that's that soreness that you're going to feel. Lactic acid within an hour or so after exercise, it's going to be transported away by the blood. And it's not going to cause these long-term issues. So whether lactic acid plays any role in the development of fatigue at all is really, really questionable. It's probably not playing any role in that soreness, that burning that you're feeling when you're working. That's friction between your muscles and the underlying bone and the connective tissue. That's leading to that. Another type of fatigue, real quickly, central fatigue. This may involve a reduced transmission of action potentials from the brain to the spinal cord out to our muscles. We may see a reduction in signaling to skeletal muscles that actually happens before the muscles get tired as a way to protect the muscles against excessive damage. Where just here, the brain and spinal cord, we start to involuntarily reduce the generation of action potentials going out into our muscles. That's when our fatigue is slower performance down. And there's another type of fatigue that I haven't mentioned up here. This is probably the biggest one when you're exercising. It's probably a type of fatigue that we start to feel as the semester goes on. What kind of fatigue am I talking about? Mental, psychological fatigue. It's that feeling, that's one of the big things you gotta get over when you're exercising or when you're taking a class, that feeling, oh my God, I can't do anymore, I can't go on anymore, I've got this much more to do, it's not gonna happen. That psychological fatigue can certainly decrease your capacity to do work. It can certainly reduce the efficiency of your performance. That whole not just physical activity, but mental activity as well. So with that, as we're ending, quite that mental fatigue. And how I feel today, coming back from spring break, it's tough coming back from the week, being away from class. I feel like I'm starting